Okay, welcome to day 76. Last class, we worked with the Pythagorean theorem. The first page, page 2 in your packet of the actual homework, is asking you to apply the Pythagorean theorem in a way that involves a little bit of solving. So for example, well, what is the Pythagorean theorem? Really, I didn't drill in that it's more than that, huh? If I have a right triangle where the sides are A, B, and the hypotenuse is C, then it's A squared plus B squared equals C squared. This is part of the theorem, the hypothesis. So please keep that in mind as part of it. How could I then use that to solve for X here? Ben? 10 squared plus X squared equals 25 squared? Okay, so you're thinking we need a new variable for this length. Why couldn't we have gone directly to X?
X squared plus Y squared equals B squared.
Because in order to use Pythagorean theorem, you have to have two sides of the triangle, right? Like if I have 28, there's a bunch of answers that could be these two. So the Pythagorean theorem only works when you've got, for instance, two answers. If I had 15 and 28, I could find the third. Agreed? And in fact, this is interesting in light of what you just did for the warm-up. Because in the warm-up, what you were doing was you were creating a system of equations, right? Like 1a plus 2b plus 0c plus 1d equals 41. How many variables are in this? A, B, and D in this case. Like this is Albert, and this is the pi symbol, and this is the apple pie, and this is the circle. With three variables, is it possible to solve this with one equation? Let me take you back to your algebra. If I have x plus 2y equals 5, and I have 3x minus y minus 3x minus 2y equals -1. How do you solve that? Come on, guys, focus on me. If I have a linear equation, x plus 2y equals 5. I'd move x to the other side over here. Why?
Isolate y.
Okay, why is that important?
Wait, you want to solve
okay, I do. So is it possible to solve for this equation? Find out what x is and y is. Just with this information. No?
But you can do something like either y or x is 0.
Okay, but does that solve for this equation? How many solutions are there to this equation? Is there just one? This is a linear equation. If I figured out exactly how to graph it, and that might be what you were suggesting, is you move the x over and then divide by 2, and you've got y equals mx plus b. Or like Will suggested, if you put 0 for x, you find the y-intercept, and you put 0 for y, you find the x-intercept. Regardless, what this thing does is it draws a full line. This is a linear equation. And every single point along this line represents an ordered pair of x's and y's that make this true. If x is equal to 5, then y is equal to 0. If x is equal to 0, then y is equal to 2.5. Right? There's an infinite number of possible solutions for this, which is why in algebra, you were graphing this as a way of showing what it is. It's all the possible points. I cannot find a single solution for this because there's too many of them. But if I also then add a second equation in, now could I find a point of intersection? If I draw this other line, I find that there's only one point that satisfies both of them. In other words, when I have two variables, I need two equations to put them together and solve. So when we were doing the warm-up and you had 1, 2, 3, 4 equations, 4 variables, you really needed 4 equations, and there would be a way to put them together in pairs, eliminate. You might remember elimination as one of the options as solving this. Since the y's eliminate by just adding straight down, I can add straight down, and I get what x is. Plug it back in, and I can solve for y. So 2y equals 4, so y is equal to 2. So the answer is 1, 2. That's the point of intersection. But in the same way, I've got 3 variables here. Even if I plug in one of them and say a squared plus b squared equals 28 squared, how many variables do I have? 2. Can I solve this with one equation? No, I'd need a second equation with 28. Otherwise, there's just too many choices. So all this to say, you were right to recognize that I can't solve for x right away because I have 2 missing sides. So you created y as this side, and then you said that means for this right triangle, I can say 10 squared plus y squared equals 25 squared. 100 plus y squared equals 625. Subtract 100, and y is equal to 525. Oh, y squared. Okay, how's that help us? So you're saying I should say y is equal to square root of 525. Now, on this homework in general, I want you to simplify whenever you can. I want you to show me that you know how to simplify radicals. So in this case, I'd take 525 and factor it. It's 5 times 105. This also ends in 5, so 5 times 21. So this would be the same thing as y is equal to square root of 5 times 21. So how do I express that in a simplified form? Good. 5 root 21. Now I'm just going to leave that alone for a second. I really wanted the value of x. If this is 5 root 21, I can say that this side squared plus this side squared equals this side squared. So x squared plus 5 root 21, I'm going to make sure I put this in parentheses because it's the whole side being squared, equals 28 squared. X squared plus, what is 5 root 21 squared? Good. You know it's 525 because we just square rooted it to get that. If you forget how to do that, what you do is you're multiplying 5 root 21 times 5 root 21. It's going to be 5 times 5 is 25. Root 21 times root 21 cancels the square root sign. So you get 121 out of it. 25 times 21 is equal to 525. What is 28 squared? Something less than 900, but 784. I subtract 525. I get x squared is equal to 259, which means x is square root of 259. And you should see if you can simplify that. Turns out this one doesn't simplify. As a result, that's a good answer. If you want to be really good, you should give me both the precise answer and then take your calculator and figure out what the square root of 259 is as a decimal approximation and round it to the nearest hundredth. Now you're giving me a ton of information, both the precise value and then a squiggly to show a decimal approximation. So, it's about 16 feet. If I was going to walk it, I'd want to know that. So this page is all just applications of Pythagorean theorem. Make sure that you draw the picture down here, show your work, and give me a simple answer, simplified, and rounded to the 100th, please. Just like we did there. Any questions on applying the Pythagorean theorem to solve these problems? Okay, let's get to the new stuff. Just like we were talking about a moment ago, the Pythagorean theorem only allows us to solve problems if we have 2 sides. So if I have a right triangle and say 10 is the hypotenuse, can I find both x and y with the Pythagorean theorem? No, not enough information, two variables. I'd need two equations. But it turns out that, well, this triangle wouldn't help us much. There are some triangles where one piece of information about the sides would be enough. And I know I'm supposed to say that all triangles are created equal, but I'm a little bit biased. I believe that there are better triangles and worse triangles. There are some that I'm going to call special right triangles. There's two of them. One of them is when I take a square and I slice it in half. And one of them is when I take an equilateral triangle and slice it in half. If I take the square, what do I know about a square? Four right angles. Sounds like a rectangle so far. What makes it a square? All the sides the same. Okay, so I'm going to pretend that this side is 10. That makes this side 10, and this side 10, and this side 10. So now to turn it into a triangle, I'm going to have to cut through this diagonal here. Do you see the triangle I'm now looking at?
Yeah.
Tell me about that triangle. Can you classify this triangle for me? Well, that would give us an area. It's a right triangle. Good, because when we classify, there's two types, right? There's by angle and there's by side length. By angle, you've identified the biggest one as right, so this is a right triangle. By side length, is it equilateral? No, equilateral is valid for sides, but that would require that all three sides are the same. Are they all the same? It's isosceles. Why?
It could be a right triangle, but it could also be isosceles because 10 and 10 are equal. Because it's a square and we cut it in half, the two base angles are equal.
Good. Because it's a isosceles triangle, these two base angles are the same. If this is 90 out of the 180, that leaves these to each be 45 degrees. So it turns out we're going to call this triangle a 45, 45, 90 triangle. This is one of our special right triangles. And what's cool about it is that we can actually discover information based on just one side. If I give you a 45, 45, 90 triangle, and I tell you that this side is 6, I can find the other two sides. Can you? You sure? Go ahead, Kiki. Go ahead, Kiki. Hold on. Right? But how do we find the third side? Pythagorean theorem. No, 180 is the angles. But now that I know two of the sides, can't I find the third?
6 squared plus 6 squared.
Good. And I'm going to simplify this. You'll see why it's important to be able to simplify this stuff in a moment. To simplify 72, I'm going to say 8 times 9, 4 times 2, 3 times 3, 2 times 2. So this is the same as 2 times 2 times 2 times 3 times 3. Almost. A 2 out front and a 3 out front and a 2 on the inside. So 6 root 2. Now, any guesses? If this isosceles right triangle had a 6 and a 6 as the sides, and the hypotenuse is 6 root 2, what are these two with 10s? What are they going to make the hypotenuse? 10 root 2. What if I had another one where I told you that the side length was 3?
3 root 2.
The hypotenuse is 3 root 2, and this side is 3. How do you know that's true?
What's the third thing here?
But I haven't told you any theorems for special right triangles. Pythagorean theorem is not what we're doing here. It's a piece is more than that, right? You're saying, okay, if isosceles, then these sides are the same. If these are the same, then I can do Pythagorean theorem. But what we're trying to do here is effectively create a theorem, a rule that applies every time. And if I just show you 3 examples, is that a pattern enough for you to say it always works? No, that's inductive reasoning. We don't do that. We want the good deductive reasoning. But what if I tell you that this side is A? Because it's isosceles, don't I know that this is A? So if I want to find X in terms of any value A, not just 6 or 3 or 10, I can set it up with variables. A squared plus A squared equals X squared. That means 2 of these A squareds make X squared. When I square root both sides, I get X over here. Over here, I get 2 times A times A. What's pairing up? So those come outside and I get A root 2 equals X. In other words, anytime I've got this special right triangle, this side is going to be root 2 times either of those sides. So here, for our little main idea notes, if the leg here is A, then we know this is A, and the hypotenuse is what? Nope. A root 2. So how does that apply? Look at number 1 here. If this side is 8, that'd be 8 also, right? And what about Y? 8 root 2. That is the skill we're doing here. It's looking at a triangle, deciding if it's a 45, 45, 90 triangle, and if so, figuring out the pattern of the side lengths. You do number 2, please. Okay, what do we get for X? Good, 25 root 2. And Y is 25, easy peasy. Can you do 13, number 3 the same way? No. Yes. So we have to ask ourselves, what were we doing when we went from 25, from the side length, to the hypotenuse? Because now we're going backwards. So what did I do to turn this into 25 root 2? If somebody did not understand what you guys have just learned, where this is 25, how would you tell them what to do to get to this? Okay, but tell me like what you're doing. To go from this to this, what are you doing to 25?
25 squared, 25 squared, X squared.
No. How do you find out what this is?
7 squared plus whatever.
You guys are way overthinking it. Tell me what the answer is here. 7 root 2. How did you do that? I put a little root 2 right next to 7, right? But mathematically, it's not like put it next to it. What are you doing? What's the operation between these two?
Oh, 49 times 2, something.
No.
Like,
multiply. Thank you. In other words, to go from the side length to the hypotenuse, we're multiplying by root 2. Because this means 7 times root 2, doesn't it? Therefore, if I want to go backwards, to go from this back to X, what do I need to do? Divide it by. So the answer for here is 19 divided by root 2. That is the answer. However, you can't have a root on the bottom. We learned that 2 classes ago when we talked about radicals. So how is it that I simplify 19 over square root of 2? Okay. If I were to square both of them, I agree with you that the denominator would no longer have a radical. However, is that a valid thing to do to a fraction? Just a second, Gus. Just a second. If I take a fraction of 1/2 and I square it, I would get 1/4. Are you telling me that 1/2 and 1/4 are equivalent fractions? No. So your idea to square it, while it would fix the issue, would change the value. So let's not do that. Gus just suggested multiplying by the reciprocal. If I take a number and I multiply it by the reciprocal, does it retain its original value?
Does it?
No. If I took 1/2 and I multiplied it by 2,
You get 1.
you'd get 1, which is not the same thing as 1/2. The giant 1. Now we're talking. There's something we can multiply this by root 2 on the bottom, which will clean that up. And if I do it, I got to do the top also. So 19 times root 2 over on the bottom, because these are both on the inside, they get to circle and come out. And so I'm left with 19 root 2 over 2. That's my final answer. The real answer is because square root of 2 is an irrational number. That means, like pi, the decimal never stops. It goes on forever. It never repeats. You can't ever say, good, that's the answer. And when you divide, you're saying, I'm going to split it up into that many pieces. And it's impossible to split it up into an indeterminate number of pieces. But just like we look at, if I give you 10 over 20, are you happy with that fraction? It's not simplified. You'd want to make that 1 over 2. In the same way, going forward, whenever you see a radical in the denominator, that should spark you the same way as, hey, that's not okay. I can't leave it like that. So here, this is going to be 19 over 2 root 2. What about y? Same thing, because this is an isosceles right triangle. All right, now I told you in the beginning that we had 2 of these special right triangles. One comes from a square. This one will be called a 45-45-90 triangle. One comes from an equilateral triangle. What do you know about an equilateral triangle?
They're equal.
Angles are equal. And if they all add up to 180, what size is each one? 60, 60, 60. What about the sides? They're all congruent. So like maybe 10, 10, and 10. And again, I'm going to split this triangle in half. This time this way. And when I drop an altitude, that makes it a right angle here. So now what I'm looking at is a different special right triangle. This time it's got a right angle that I just created, the 60 degrees that was always there. And now I've split the top angle. Instead of being 60 on top, that's now split into what? 30. In other words, this is now going to be called a 30, 60, 90 triangle. And it's our second special right triangle. You'll remember that this side of the equilateral triangle was 10. How long is this bottom side? It's 5. Doesn't it get split exactly in half? Because I've got angle, they're both 30, shared side, reflexive, angle 90 degrees. These 2 triangles are congruent. By CP, CTC, both sides are congruent. Therefore, that's a 5. Now, can I find this missing side using Pythagorean theorem?
Yeah.
Yes, do it. Go. Simplify your answer. We cut an equilateral triangle to get this. Okay. Did we get 5 root 3?
Yeah.
All right. Would anyone like to hazard a guess as to what's true about every 30, 60, 90 triangle? Whatever this side is, don't we know this is going to be half as much? Because if it were an equilateral triangle, whatever this is gets cut in half. So if this starts off as A, how big is the hypotenuse? 2A. And what's this side going to end up being? Say it again, Erlin. So these are going to be the same? That didn't work here, though. We had 5 here, and this became 5 root 3.
A root.
A root 3. The 3 comes from the fact that we had twice here that gets squared, which makes it 4 times, and you subtract 1, which makes it 3 times. In other words, let's say we want to solve this. I'd say that x squared plus a squared equals 2a squared. X squared plus a squared equals 4a squared. Subtract 1, I get x squared equals 3a squared. When I take the square root, I get 3 times a times a. So x is going to equal a root 3. It'll be 3 every time it's a 30, 60, 90 triangle. So that's our second thing here. If the shortest leg, this is the hardest part with this one. Remember my dinosaur analogy?
Yes.
How can you forget that? Sleepless nights. If I've got a caveman sitting on the side of a cliff over here, and a dinosaur comes up ready to chomp him, how does the caveman save himself? He puts a stick or a bone in his mouth. Now the dinosaur's like, and he scampers away, right? And the point of this was that opposite the smallest side, smallest angle, when the mouth is small, you put a small stick. When the mouth is bigger, medium, you put a bigger stick. And when the mouth is the biggest angle of a triangle, it's opposite the biggest side. So the shortest leg is opposite 30. That's going to be your A. The longer leg, which is also the mediumest side. Nope. The medium side would be A root 3. And the hypotenuse, which is the longest, would be 2A. Now, pro tip, this is where everyone makes mistakes. They mix up which one goes on the hypotenuse and which one goes on the leg that stands opposite the 60 degrees. How do you know which one of these is bigger? Can you guys please stop talking? Once again, we're on recording for all to hear forevermore on YouTube. How do you know whether A root 3 or 2A is bigger? Well, 2 is the square root of what number?
4.
4. So if I treated this as A root 4, isn't that equivalent to 2A?
Yeah.
And isn't A root 4 bigger than A root 3? Yes. So you know that this has to be the biggest side, which means it's got to face the biggest angle, which is the 90 degrees. So let's take a look. Number 4. Are we given the little bitty baby side?
Yes.
Yes. Therefore, x, which is the mediumest side, should be what value? Or in this case, 5 root 3. And then y, the hypotenuse, would be 2 times 5, which is 10. Go to number 6. Oh, no, they made it so much more difficult because they didn't give me the baby side.
Oh,
Nope. Sophia, why? This is the side that's supposed to be 2A. It's the hypotenuse. So if 2A is 32, then 16 is A, and that's our shortest side. Very good. Which means y is what? Yep. Seven is the exact same as that. Take a look at number 9 for a second. X is 9. What are you, crazy, Gus? How'd you get that? Yeah, this is the side that's supposed to be a root 3. So if X were 9, then you multiply it by root 3, you get 9 root 3. That's exactly right. Y is 18. But what about number 8? This is the humbler. The hand goes up and then the Really good. It's got to have a root 3 in it, so you multiply it by a root 3 to make the root 3 go away. But again, since I'm multiplying by root 3 to go from here to 20, what do I do to go from 20 back? Divide. So this is 20 over root 3. Are we satisfied and happy with that answer as it's written? Big one. So that gives me 20 root 3 on top, and root 3 times 3, which means the 3 gets to come out, 20 root 3 over 3. That's the answer for Y. Now, some of you might call that an ugly number. Some of you might call that a particularly beautiful number. But it is definitely intricate, complicated. In fact, it's irrational. So, it's exactly right. Now we're going to double it. Do we double the 20, the root 3, the 3? No. It's just the 20. Because we don't multiply what's in the parentheses by what's, or the bracket, the square root symbol, by things that are on the outside. So when we double this, we're going to do 2 times 20 root 3 over 3. And that's going to become 40 root 3 over 3. How are you feeling about this? 5, I won. I win. I will never lose again. 3, I've got a shot at winning this. I'm optimistic. 1, I quit. Okay. Your homework today, for the rest of the period, is to practice these. And don't forget to finish up the applications of Pythagorean Theorem. This packet is your 76, including the warm-up. Submit it when you're done. You have the work period. Just a second, please.